So if you're ready, then for the last invited talk of the day, in case, is Dan Christensen from Canada, who's going to talk about diagram chasing in the Coq-HoTT library.
Great. Well, thank you very much for the invitation to participate here. I've enjoyed the talks I've been able to attend, and I just wish I could be there in person and also participate in the coffee breaks and the informal conversations, which are so important at this kind of event. In any case, I'm going to be talking about some work that's a bit more recent than what Nikolai just spoke about. I was making improvements to it even yesterday, so it's hot off the presses. I'm going to talk about this technique called diagram chasing. It's a common thing used in homological algebra and in classical mathematics. And I'll describe a method that Thomas Thorbjornsen and I, my PhD student and I, have come up with that makes this work very smoothly in the Coq-HoTT library. And if you want to see these slides or the GitHub repo, you can go to my webpage. They're available there. So let me start by making a few comments about Martin's work. One of the things I love about a lot of his work that I've read is that it often starts with a very simple question and then leads to some very beautiful theory coming out of it. In particular, I've looked at his work on injective types and on searchable types or compact types, and I think they're great examples of this. Some students in the course I taught formalized these results for the Coq-HoTT library. That was where I learned more about them. We've also heard other examples of this during this event, including in the last talk. So this talk is sort of similar in that I start with a very simple sounding problem, but instead of developing any theory, there's not really any substantial theorems in what I do, but it's more of a pragmatic tool that actually just works to make this technique very efficient. Okay, so what is diagram chasing? So this is a technique that's used when you're trying to prove things about abelian groups or R modules or more general objects. I'll say a bit about the generality in a moment. And let me just start with an example. So suppose you've got a diagram like this where the three squares commute. I'm going to assume everything's abelian groups just for the example, but the whole point of the talk is to be able to generalize this. And in this diagram, we assume that this map is an epimorphism, this map's an epimorphism, and this map is a monomorphism. And we assume that the rows are exact, which means that if you have an element here that goes to 0, then it has a preimage. In HoTT, we would say it merely has a preimage. And that's true at this position and this position and this position for the horizontal rows. Then the conclusion is that this map should be an epimorphism. So let me give you the way we would typically prove this on the blackboard. And I guess I had a bit too much time on my hands because I made some fancy slides here. So to try to prove that H is an epimorphism, we should start with an element little c prime in big C prime and try to find a lift of it through H. One of the nice things about this technique is you almost have no choice about how to do the proof. What can we do with this element? We can't go backwards because we don't know that it goes to 0. We can't lift here because that's what we're trying to prove. The only choice is to move it forwards. Now we've got an element. Going backwards would be useless because that's where we came from. Going forwards will give 0 because part of being exact is that the composite of any two maps in these rows is 0. I didn't say that explicitly. So the only choice is to lift it, which we can do because we have an epimorphism. So we assume we have a preimage here. No reason to go down because that's where we came from. We can't go back yet, so the only choice is to go forward. Again, the only choice is to go forward. But since this square commutes, and since the composite of these two maps is 0, we learn that E goes to 0. This map is injective, so we learn that E is 0. And now we can use the exactness here to get a preimage of little d that we'll call little c. And you might hope that we're done, that the image of this little c will be c prime, but there's no reason for that to be true. So the thing you do when you get something that may not be correct is you look at the difference. So we consider that difference. Well, first observed by commuting of the square, our C double prime also goes to D prime. So we look at the difference. The difference will go to 0. That means that difference has a preimage by exactness here. This map is an epimorphism, so we have a preimage, and that gives us a new element. I'm going to move this data over to the side just to make some room. So that data is just copied over here. We get a new element here, and because the square commutes, it hits this element. And then it turns out that if we take the sum of the element we originally had there and our new element, it will go to the sum of this and this, which is exactly C prime. Okay, it's a very long argument, but it's completely sort of a follow your nose argument. And that's the kind of thing we'd like to be able to do in a proof of system. If you were doing this in HoTT, you would need to say merely at many places. We would merely have lifts, and then you'd need to strip those truncations off at various stages, but it would be essentially the same proof. Okay. So the challenge is that there are many situations where we know classically that this theorem is true, but we don't have elements for our objects. We're in some kind of general abelian category where the objects in the category don't have elements that you can chase around a diagram. If you know what abelian categories are, that's great, but in fact, we're going to do it in a more general setting. We only need these two assumptions. So we're going to work in a category that's enriched over abelian groups, so that if we have parallel arrows, we can add them and subtract them, and that it distributes over composition. And we're going to assume that pullbacks of epimorphisms exist and are themselves epimorphisms. Yeah. And that's all we're going to need. So that's true in an abelian category, but there's lots of other situations. So just as some examples, so any abelian category like abelian groups are modules, sheaves of abelian groups are modules, abelian group objects in a topos. One that comes up in certain arguments is the category of left exact functors from an additive category to abelian groups. You can take categories like torsion-free abelian groups. Those aren't abelian, but they do satisfy these conditions. So there's a lot of settings that our approach will work in. So there's a lot of past work that I'm going to first summarize about what people have already tried to do to generalize this diagram chasing technique. They usually work in abelian categories. So that'll be the framework for when I'm talking about the background. Okay, so the first thing you might do is simply use generalized elements. So take the elements of A to be any object P along with a map. So in effect, we're using the Oneda embedding here. And that doesn't work because the Oneda embedding isn't exact. So the problem is that if you have an epimorphism and you have a generalized element P mapping into A, it won't lift to B unless P was projective. So just using generalized elements doesn't solve this problem.
Does it work to use generalized elements only when P is projective, or does that not determine the group?
So the question was whether we could just use generalized elements with projective domains. And the problem is many of these categories don't have any non-zero projective objects. So that also wouldn't work. So a common technique is one that MacLean proposed back in his book on categories for the working mathematician in 1971. He took equivalence classes of generalized elements, where he said that a generalized element is equivalent to any precomposition of it with an epimorphism. And then he took the equivalence relation generated by that. And I'll show you on the next slide why that equivalence relation is very nice. And he showed in his book that you can prove two standard diagram chasing lemmas. But the one that we just proved, he left that as an exercise in that section of his book. And I don't think it can be done with his setup. There are a couple of questions online where people have discussed it and not found a solution, and I couldn't find a solution either. the issue is that we had to subtract elements and add elements in our proof. And MacLean has a way to sort of subtract elements in a very special situation, but no way to add elements. And in fact, in his setup, every element is equal to its negative. So it's really an awkward place to do anything with an abelian group structure. Nevertheless, this has been used. So I'll give citations at the end, but it was introduced into Lean in MathLib by Marcus Himmel and in Coq and Unimath by Tomi Panilla. And you can prove some of the results with it. It's a nice setup, but I would really like to be able to add and subtract elements so that first proof could go through just like I gave it. A completely different approach that is often used in classical mathematics is to observe that any nice enough abelian category can be embedded exactly into a category of R modules. There are various results of this sort. The most famous is the Freid-Mitchell embedding theorem. But the proofs of these results are not constructive. I'll cite a paper at the end by Martirulli, that actually shows that certain steps in the proof are not constructively valid. So we don't want to rely on an embedding theorem like that. So let's think more about MacLean's idea, because it's going to be the basis for what we do. What we're going to do is use this equivalence relation, but not work with the equivalence classes. Instead, we'll work with representatives. And the reason this equivalence relation is a good one is suppose you have a generalized element of B and you have an epimorphism. As we said, we don't expect a lift in this diagram. But if we take the pullback of this diagram, we'll get a picture like this. And because pullbacks of epis are epi, this map is epi. And this new generalized element, when I compose it with F, it is equivalent to the generalized element we started with, because the relation says if you can pre-compose with an epi and get an equality, the square commutes, of course, then you have this equivalence relation. So up to that relation, we do have lifts of generalized elements through epimorphisms by taking pullbacks. So that's the motivation for that relation. So I'm going to give a name to this. So if we have two maps, I think of this one as a generalized element, and this is a map. The type of MacLean lifts of the element through the map is a choice of an object, a choice of an epimorphism, a choice of another map, and the square must commute. I do not require the square to be a pullback. That's how we prove existence of such lifts when F is epi using pullbacks, but the general definition doesn't require it. Okay, I'm going to repeat that on this slide. And MacLean showed two facts. So the first is that you can characterize the epis as the maps for which the generalized elements all have MacLean lifts. And you can characterize the exact sequences as the pairs of maps that, well, they have to compose to zero, and every generalized element in B that goes to zero has a lift. So it means this lifting condition that he came up with is a really good one to work with when you're dealing with epimorphisms and exact sequences. You can also characterize the monics, the isomorphisms, and the zero maps in this way. So as I mentioned, though, you can't add and subtract maps very well with his setup. So there's an unpublished paper of Bergman, which I link to at the end, which suggests what you should do is use this approach, but keep track of all the epimorphisms that arise along the way every time you do a lift. And you can do that, and it does work, but it requires bookkeeping. And that was also added to MathLib a couple of years ago by Joel Ryu. But I'm still aiming for something where we don't need to do this kind of bookkeeping. So I'm going to illustrate our method by an example. So remember the diagram we had in the first argument. Let's pretend we're in a proof assistant here. On the left, I'm going to write my context. On the right, I'm going to write my goal. So the context so far is that the rows are exact and that we have 2 epis and a mono. And our goal is that H is epi. So by the characterization of epis, it's enough to take a generalized element of the codomain here and produce a MacLane lift. The reasoning is explained down here. Next, we do the step we did before. We take the image. I've named this map now, and I call the image gamma prime C prime, and we find a lift for it because this is epi. So when I say abbreviated, I've just not put these objects in the context. So there's, of course, a couple of lines I've compressed here. So there's a new object P prime, an epi, and a new generalized element of D, and the image of the generalized element is our original one up to precomposing with this epi. Okay. So that's the characterization of epis again. Now, the only thing I'm changing at this stage is this one spot. You can show that if you want to lift C prime, it's enough to lift C prime precomposed with any epi. So that's an easy lemma. And now if you look at what's going on, we see C prime composed with E in 2 places. So we can generalize that. If I want to prove this goal for this particular composite, it would be enough to prove it for any generalized element with domain E prime. So I generalize that to a new term, and I also generalize it here. And now you notice that we don't use C prime or E anywhere in any of the hypotheses or conclusions. So we just clear them away, including the domain P. It's not used anywhere. And now we can just rename P prime to P, rename C double prime to C prime. And now, if you remember, the context we started with had exactly this. And our new context simply has a lift to D with the same domain, an equality exactly like we would expect when we have a lift, and our goal is unchanged. So only the last 2 lines have changed after this sequence of steps that we just did. And so our observation is really that you can do this generalization and renaming, and you can package that up in a nice tactic. So summarizing it here, so that it appears to you when you're using this that you can lift generalized elements through epimorphisms. You start with the generalized element, and at the end you have a lift of it through that epimorphism. Okay. And you do that at each stage. I'm not going to continue the rest of the proof, but every time you do a lift, you look at all the generalized elements you have, and you adjust them to have the new domain that got generated. So what we used was that when we have an epimorphism and a generalized element, lifting the composite is equivalent to lifting the original element. And we also use that when you've got paths between functions, that's preserved by precomposing with an epimorphism. And then it's a fairly simple tactic. It's 34 lines that we implemented here. That lets you do these steps that I outlined, where you use one direction of each one of these statements in hypotheses and the other direction in goals, to always ensure that all your generalized elements are precomposed with E. And once they are, then you can generalize them, rename them, and so on to do that same procedure that I illustrated. The nice thing about this is that at every stage of the proof, there's only one domain for all of the generalized elements. And when you have generalized elements in the same object A with the same domain, then you can add and subtract them without any trouble. And you also get laws like this because the additive structure distributes over composition. So with this method, you can prove the 5 lemma, well, the lemma that I stated at the beginning, which is part of the 5 lemma, exactly like I did it. You can prove the monic version. You can prove a bunch of forms of the 3 by 3 lemma. You can prove these lemmas that all have crazy names: the spider lemma, the snail lemma, the small baby dragon lemma, the diamond lemma, and there's some other lemmas that don't have cute names you can also prove. And we've done all of these, and we've checked that the proofs are essentially identical to what you would do if you were doing this in classical mathematics. In fact, they're a little bit easier than what you would do if you were doing it with abelian groups in HoTT, because the lifts that we get, they actually exist purely. Because remember, we took these pullbacks, which give you a choice of a generalized element as your lift. So you don't need to worry about propositional truncations when you lift elements through epimorphisms. So it's actually a little bit smoother than the proofs for abelian groups. In addition, we don't need to use any univalence or function extensionality, so we're working in a Spartan type theory like Martin likes. The Coq-HoTT library tracks all uses of these axioms because we like to know where they're used, and we don't need to use them. Now, for function extensionality, the trick we have to do there is we have to use homotopies everywhere where I was writing equality of generalized elements. You really use homotopies. And we work in a setup that has a wild category structure with specified 2 cells. And so we make heavy use of that. Okay, so the formalization, I'll break it up into 3 parts. There's a link here. The setup that just makes the axiomatic framework that we're working in and proves the various lemmas about enrichment and so on. That's around 700 lines of code. Then all those lemmas with cute names, they're about 765 lines of code. And then there's another 900 lines that was just background material that needed to be added just to support this setup, such as saying more things about pullbacks in wild categories and so on. I guess I have a few more minutes. Some limitations. We're using a tactic for this. And this goes against what Martin would like. I know his proof assistant of choice is Agda. I don't know how one could do this without a tactic.
It does have some more meta programming.
Yes.
Yeah, so it could be possible. I don't know Agda well enough. So to me, this is a sort of an open question, whether there's some way to make something as easy as this in Agda. Another issue is that in all different frameworks where you use generalized elements, it's very hard to define a map by saying what it does on generalized elements. So we have some hopes of making this work by keeping track of the sequence of epimorphisms that arises during an argument, but that's work for the future. I will also mention that there's work by Renaud, Lafont, Mabubi, and Piqueras, work in progress, where they have something that's much more sophisticated than what I've described here. And it should let you construct maps and check equality of maps as well using generalized elements. So I'm very excited to see how that comes out. And then I will end with a list of references. These are the people that I mentioned during the talk. If you download the slides, you can click on the links to get to these results. And I will end by saying thank you for listening and another happy birthday to Martin.
Ingo made a comment.
Hi, Dan. Thank you very much for both the happy birthday and for the talk. So maybe you can go back to slide 12 again.
Yep.
So
Ingo in the comments.
Sorry, just please wait for the question to finish, okay?
Oh, okay. I didn't hear that there was a question.
So this is all that you did here kind of reminds me of what Steve Vickers did in his talk. I don't know if you had a chance to attend it, but he proved something about locales, pretending you have points. And in particular, sometimes you can use the lambda calculus and so on. Now here you wanted something simple-minded and pragmatic that you got, but I wonder whether actually this can be seen as a kind of a model construction. So you extend your categories so that you have projectives and then, something like that. Maybe that's a better question for the proof theorists in the audience. But, yeah, it seems to me like you're constructing an auxiliary model to make the reasoning simple.
Yeah, it's possible. I would love to have a theoretical basis for it. As I said, right now it's more of a pragmatic fact that in practice, when you do these proofs, we observed a pattern in how the generalized elements are used, and that they could always be replaced with new elements with common domains. But I would love to have a more theoretical understanding of it.
There's a comment by Ingo in the chat about how it's using the internal language of some sheaf topos. So maybe this is the kind of thing that you're thinking about. Yes, Paul?
Yeah, I've read a little bit about that, and I don't know exactly how it corresponds, but I suspect it's certainly very related. We need much less than a regular category for this, so that's one reason I'm not sure it exactly matches, but it's probably related.
Can you hear me without the microphone?
Yeah.
Yes.
Okay, so since I've been in computer science departments, I've forgotten how to do subtraction. I tend to work in categories more like toposes than abelian ones. But I've done quite a lot of work with factorization systems, and I'm wondering whether the kinds of lemmas you're trying to prove here can be reformulated with factorization systems rather than. I'm not quite sure how exact sequences work with factorization systems, because I'm trying to think while I'm listening to your talk. So maybe there's some different kinds of diagram chasing using factorization systems that you could try out using your methods.
I don't know if this exactly answers your question, but there are approaches to doing homological algebra that first prove a couple of lemmas some way, and then they organize everything so they can just use those lemmas to derive all the other ones. So I don't think it's a factorization system result, but it's at least a similar idea that you try to package everything up in a few lemmas that you have to find some way to prove, and then you can reuse them. But most of these lemmas, if you do them with the diagram chasing approach, there's just no thought required. Like you can just plug away and do it. So that's why I really like to be able to do it the old-fashioned way, in a sense.
Thanks for the talk. It was really interesting. This is maybe a question more for Ingo, making that comment about internal language in a sheaf topos. To check my understanding, is that does it mean that the embedding from the original abelian category into the sheaf topos is going to be exact if in the internal language you're able to sort of add, subtract these elements, these fake elements?
This sounds like a question for Ingo.
Ingo said yes in the comments.
Okay. I can't track the chat while thinking.
You have the online question.
Yeah, I think it's gone.
Oh, okay.
Okay, so let's thank Dan again.
Thank you. If I may, can I say one more thing? As the last speaker, I think we should all thank the organizers for this wonderful event.
I believe Martin wanted to say a few words.
Yeah, I had a speech, but because there were so many talks, I'm not going to give it. I'm going to be brief. So again, it has been said many times, but it doesn't hurt to repeat. So thanks, Tom. Thanks, Eric, for organizing this. And also, thanks for the many nice talks, remembering things from the past. Some of which I remembered, but I didn't remember that I remembered. It was good to hear them again. Yeah, and another thing I wanted to say is that there are a lot of students here. So, and I love teaching. Doesn't matter if it's very basic, like teaching the definition of a limit to a student, or talking about toposes or whatever. I love teaching. And these often resulted in surprises in the future, like where are you, Nikolai? That's one example here, but there were many other examples.
Thank you.
Okay, I don't have anything to add to that.
Was there a plan to get a drink?
You can lead the plan to get a drink. How about that?
Just volunteer. So,
Beyond the campus or?
yeah, there's a bar on campus.
Yeah.